If we want to calculate the entropy of a statistical mechanical system, then we use the general formula for this, which reads S equals KB ln omega. And omega is just counting the number of states, and in the case of a monatomic gas, for example, which is the subject of this video, a non-interacting monatomic gas, then this depends on n, that's the number of particles, on the volume V, and on the energy U. And omega is the multiplicity, and that's the number of states that we can find at particle number n, volume V, and at energy U. The presence of omega in this expression tells us that we need to count states, and so first we need to specify what a state is. Well, if we have a single particle running around in some volume, then its state is given by its position and its momentum. So for a single particle, we have R and P, and that already poses a big problem because these are continuous integers and it's very hard to count states described by continuous parameters. We cannot count continuous variables. This problem was addressed by Ludwig Boltzmann. He recognized that it's impossible to count continuous states, and he thought of the following. Let us think about one particle in one dimension. And this particle is characterized by some x coordinate. That's the position in a one-dimensional system, one particle. And it has a momentum p. And so, realizing that he couldn't count the states, he thought of the following. Let's just divide up this space into small boxes. So we proceed as follows. Etc., etc. We do the same for x. And then if we need to count the states, it simply boils down to counting boxes. And of course you can justify this because in any experiment, x and p are subject to uncertainties. There is always some uncertainty, and you can only distinguish x's and p's that are sufficiently far apart. And so that's the reason why Boltzmann thought, well, why not introduce just these small boxes so that we can count. Here we have a better rendering of the idea, and you see that we have small boxes which have a width delta x along the horizontal axis, which is the x-axis, and delta p along the vertical axis. Of course, we are not interested in one particle in one dimension, but n particles, where n may be very large in 3 dimensions. And then the boxes are characterized by a width of the x component of particle 1, that's delta x 1. And then we have the px component of particle 1. Then we have the y component, delta y1, delta p y1. And we continue in this way, so we arrive at particle 2, particle 3, and we have delta zj, for example, delta pz j, and then finally we go up to particle n, delta xn, delta pxn, delta y, and delta pxn, pyn, delta z, n, and delta p, z, n. And so in total, we now have, if we would count the coordinates, we have 3 spatial coordinates per particle, and we have 3 momentum coordinates per particle. So in total, we have now 6 n coordinates. And we can denote those as r j alpha, that's the position component where alpha denotes x, y or z, and p j alpha, where alpha again denotes the x, y and z, and j, that is the particle index, and it runs from 1 up to n. In fact, the space of the 6n coordinates is called the phase space. The phase space is 6n dimensional, so if we take a volume in that space, we can denote it as V 6n. And if we want to count the number of states in that volume, we need to divide by the box size in 6n dimensions, and that's delta x times delta p to the power 3n. Obviously, if we do this, it seems that we get some arbitrary number because the delta x and the delta p were not fixed. But fortunately, Heisenberg, a great quantum physicist, has imposed a fundamental limit on delta x times delta p, because these two will not exceed h, which is Planck's constant. So delta x, delta p, they should always be greater than order h, where h is Planck's constant. So we can now conclude that the number of states within a volume in phase space volume can be written as that volume, which is 6n dimensional, by h in the power 3n. However, the fact that we can count numbers of states within a volume doesn't really solve the problem, because we need to find the states that are available at a certain energy. And if we have two momentum coordinates, let's take that as an example, we call them P1 and P2. P1, P2. Then the kinetic energy of these is P1 squared plus P2 squared, and if we want that to have a fixed value, then we are on a circle, like this. And if we have now boxes in this space, then it's not so clear what we should do. Well, probably we should take all the boxes that are covered by this circle. But obviously the way, the radius of the circle, if we vary it a little bit, because the boxes are differently aligned each time, there will be some noisy like fluctuation in the number, and it's not clear whether we have the right number. Now in the end it will turn out that for large dimensions this doesn't matter, but what we do in practice is that instead of taking just a sphere which is a line with zero width, we take a spherical shell. So we are taking another sphere which is a little bit larger, and the shell in between is what we are interested in. So this is the idea. We take the thickness of the spherical shell to be something like delta p, a different delta in order to distinguish it from this delta. This is the box size, and this is the shell size. We take the shell a lot thicker than the box size. And then we count the number of boxes that are inside this shell volume, and then we divide in the end by delta p to have something which is independent of how thick we made the shell. So how do we now calculate the integral in the 6n dimensional phase space, which is spanned by the momenta and by the positions of the particles? Well, that is a 6n dimensional integral, which looks as follows. It's first the integral over the momenta of particle 1, etc., up to the momenta of the particle n, and then the same for the coordinates. Where we should realize that in this case each particle is bound to be in the volume V box. I call it now VB in order to distinguish it from the 6n-dimensional volume. And this VB is the volume for each of these particles. So if I calculate the second integral, it will simply give me a VB to the power n, because we get a factor of VB for each particle. And in principle, if we need to be inside such a shell, that means that the space in the momentum coordinates is restricted. It's restricted to a shell like this. And so we have some function which depends on u, which is the kinetic energy, and it depends on the momenta of the particles. To be specific, the u is the kinetic energy. So it is simply written as the sum over all the particles of the kinetic energy, which is Pj squared, over 2m. And we can also write this as P squared. Now it's a capital P, and we divide that over 2m. And this capital P is the vector containing all the momenta of all the particles. So it's a vector of which the first three components are the momentum components of particle 1. So it's P1x, P1y, P1z. Then the same for particle 2, and all the way up to Pn. So if we integrate over a spherical shell in the 3n-dimensional momentum space, then we integrate over those p which sets are within two limits. So we have p0, which is the lower bound for the length of this vector. So that should be smaller or equal than the length of this large vector p, and that should be smaller than P0 plus a little bit, and we call that delta P, where we use a curly delta in order to distinguish it from the triangular delta that we used for the size of the boxes. So it's not this delta, but we have now a lowercase Greek delta. So what we need to do now is the following. We need to integrate here over all these p's. That's the same as an integral over the space spanned by these vectors, capital P, but they should be restricted to this condition. So that means we are integrating them within a spherical shell. And so what we need to find here is the volume of that shell. And we shall not really calculate that integral in detail, but we shall use that the volume of such a spherical shell is the area of the shell times the thickness. So that's the volume in the 3n-dimensional momentum space. And the area of a sphere in 3n dimensions, so the surface area of a sphere in 3n dimensions, I can look that up, and I will just give you the result here. It's S3n, and that's given as 2 pi to the power 3n over 2 times P0 3n minus 1, and this should be divided by 3n over 2 minus 1 factorial. So this is a formula that I can just look up, and I have used that here. And we have to multiply that by the thickness So this is the area. And the thickness is obviously my delta P. The delta P which I have there. So if we now combine everything, then we need to multiply this VB to the power n by this S3n and by the thickness. Then we have the volume, and we then have immediately the number of configurations, the number of states, which is omega, which we get as a function of u n and the volume of the box. And it is VB to the power n divided by h to the power 3n. It was necessary to divide by this. And then we have this s 2 pi 3n over 2 3n over 2 minus 1 factorial. We have a p0 3n minus 1. And then we have a delta p, and we had already agreed that we should calculate the number of states within the shell of thickness delta p, and then we divide by delta p, so that delta p then cancels. And so here is our final result. However, we see that it is formulated in terms of the p0 and not in terms of the u. The expression we have obtained is not in terms of u and nv, because there's no u here on the right hand side, but obviously u and p0 are related. We have that u is p0 squared over 2m, and therefore p0 can be written as the square root of 2 times m times u. So now we can write this multiplicity as follows. First we have the VB raised to the power n divided by h to the power 3n. Then we have the terms that we had before, 2 pi raised to the power 3n over 2 divided by 3n over 2 minus 1 factorial. And then we have a 2mu, that's my p0, if we raise it to the power 1/2 and then raise to the power 3n minus 1, gives me 3n minus 1 over 2. The aim of the calculation is not to find omega, the multiplicity, but to find the entropy S. But we are close, because S is simply defined as kb times the logarithm of omega. And we are going to calculate this in the limit of large n. And large n, first of all, implies that we can neglect the factors of minus 1 here, because they are negligible with respect to this n, which is becoming large. Moreover, if n is large, we can use Stirling's formula here. And then, all in all, we obtain the following result. We have an n kb times the logarithm of VB, the box size, divided by h to the third, and then we have 4 pi mu divided by 3n, and that raised to the power 3 over 2. And then there is an additional term, which is 3 over 2 nkb. This result, however, turns out to be wrong. The reason is that we have considered the particles to be classical, and if in classical mechanics we swap two particles, so suppose of all the n particles we single out particle 1 and 2 and we swap the two, then classically we get a new configuration, a new state. However, that's not the case in quantum mechanics. In quantum mechanics, the particles are described by a wave function, commonly written as psi, and we can represent that wave function as a function of the positions of the particles or of the momenta. So let's take the positions here, r1, etc. Rn. So these are our n positions. Now in quantum mechanics, if we would swap particle 1 and 2, or particle I and j in general, then we have exactly the same state. All the permutations of these labels R1 to Rn give us the same state. That's a postulate of quantum mechanics. And because we have n factorial permutations of the particles, we need to include an extra factor of 1 over n factorial into the multiplicity. So what we should do is to introduce this factor of 1 over n factorial into the equation for omega. So we have an extra 1 over n factorial here. And when we calculate s, we can use Stirling's formula in order to take that n factorial into account. This then results in the following form for the entropy. The entropy as a function of the energy, the particle number, and the volume of the box in which the particles are moving is given as nkb times. Then first we have a term ln v box divided by n. And then we have a 4 pi mu divided by 3 nh squared. So you see that this factor of 1 over n factorial gives me here an extra n. This term here needs to be raised to the power 3 over 2. And then we have a term not 3/2 times nkb, but nkb times 5/2, also arising from this 1 over n factorial. This result is a famous formula, and it bears the name of Sakur and tetrode, so it's called the Sakur-tetrode formula. And it has a nice property, which is not shared by this expression. This property is that if I double the system size, then S becomes twice as big. So let's do that. We calculate S 2U, 2N, and 2VB. Then we would hope that the S becomes twice as big. And indeed we have a term 2n times kb. Then what happens with the term in the logarithm? Well, the volume doubles, but also the n doubles. So we still have a VB over n. And the same holds for the energy, which doubles, and here the n doubles. So also this term does not change when we double the system size. And the 5/2 obviously is insensitive to the particle number, And so we see that this expression for the S is scalable. It tells us that S is an extensive variable. If we double the system size, then S becomes twice as big. So this is 2 times the S of U, N, and V. It's important to note that this factor of n factorial, which has a quantum origin, it's due to the indistinguishability of the particles, is essential to have an S which has this property. So quantum mechanics is necessary here in order to arrive at an expression for the entropy which is extensive, which means that it scales with the system size.